Well, welcome everybody. Today we'll be talking about the PE file format. Now, I'm sure most of you have probably at least heard of or encountered the PE file format, but you probably don't have a very in-depth knowledge of it. And so hopefully we can rectify that to some extent. This is a very old file format that goes back almost 30 years to 93 when Windows introduced Windows 3.1. Over the years, there have been a lot of features that have come and gone. But with the PE file format, we do maintain those for backwards compatibility, even if they have been deprecated. So there'll be a lot of things that may appear to be obsolete. There's also a lot that is undocumented. Some that serves a purpose, but we don't have the information on that. So we can also view the PE file format as a somewhat convoluted series of different data structures which together give us all the information so that the Windows operating system is able to load and manage the executable code. Otherwise, it's just a binary blob of data. So this helps provide a mechanism for us to be able to extract that data into that binary data into to make sense of it. How will this come into play with this class? Well, one particular way will be through the use of shellcodes, which we'll be getting into fairly shortly. So if you're able to somehow inject shellcode into process memory, and let's say, for instance, you get code on the stack and you're able to redirect execution there. Well, guess what? That shellcode does not necessarily, well, it doesn't, there's no necessarily about it, it does not know where to get DLLs, and more specifically, to get the APIs that are contained inside those DLLs. But we can make use of things like walking the PEB, walking the PE file format in order to get that information. And we've kind of touched upon that somewhat briefly before. And so now is the time where we go a little bit more in depth with that. So being able to understand the structure of the PE file format will allow us to overcome those initial hurdles with shellcoding, so that we can access API functions and call upon them. So really being able to understand and apply this information with exploitation is partly why we care about it in this class. For something like malware analysis, you absolutely do need to know the PE file format. I don't think it's as relevant necessarily in this course, aside from shellcoding. But we do absolutely need to have a good understanding of the PE file format. So what is it exactly? Well, it stands for the portable executable. So native Windows file format used in Windows, the PE file format will define what exactly an executable is, although it doesn't need to be that. It could be a DLL or others as well. When we run something in a utility like PE Studio, it is able to extract and parse all that information out of the PE file format. And by manipulating the PE file format, we're able to then dynamically call different APIs, different modules as need be. As I mentioned, we've talked about the idea of walking the PEB. This is somewhat similar. It's just a matter of walking other structures. You know, each contains structures, each contains members. So it really just comes to a matter of walking the different structures, walking the different members, until we're able to reach the information that we desire for whatever purpose that may be. And it's exactly the same thing that a loader does as well. So over to the right there, we see kind of a high-level view of some of the different main components. We have the DOS header, which contains the MZ, the 4D5A signature that indicates that it is a PE file. We also have next the DOS stub, which is a historical artifact, but still present. And there's a particular member in the DOS MZ header called elfinu, or elfinu, that we're able to use that to get over the DOS stub. Most of the structures and members are not variable in length, but the DOS stub, however, is one that is very variable, and so that calls for, it necessitates a specific member that can allow us to go over that. And from there, we can then descend into the PE header, comprised of things such as signatures, compile stamps, whether or not an executable is, or a PE is an executable or a DL, and just a tremendous amount of information pertaining to this section table. The section table being our array of structures that will define for us where the various sections are going to be located. So everything in the PE file format is extremely, very highly ordered, highly structured. It's not just a random assortment of instructions. We have the header comprising our first 64 bytes. Again, then that special member, the elfinu, that can enable us to jump over the DOS stub to reach the PE header. And then eventually we can descend down into the data directory, which we don't see depicted here, and we can access various different elements that we'll see in future slides here. Here we see the distinction between mapping the PE file format from disk to memory. There is a disconnect, and there are some very good reasons for that disconnect. When something goes from disk to memory, there can be things such as the stack and the heap that can come into play. There can be buffers that may be expanded in the process image. On disk, we have things such as offsets, whereas in memory, we see that they're actually virtual addresses. Over to the left there, we can see our DOS header, which consists of the first 64 bytes. So it is a complete structure. At the very bottom, we have the long address of new exec header. Another term for that is elfinu. At the very top, we have the MZ signature, the 4D5A that denotes that it is actually a PE file. And those are really, for our purposes, really the only thing of any consequence in the DOS header. And then from the elfinu, or address of new exec header, we then can jump over that, and we can get to the PE header, which here is called simply image optional header. So the image optional header is going to be one part of the PE header. And then there at the very bottom, we can get down to the highlighted image data directory. We can get to some virtual addresses, and we can then add those to the image base. And from there, we can then get to whatever the data directory in question is. So right over here will be our image base. we can descend down to here. We can go into one of these, say exports, and it'll give us one of the two members there will give us the virtual address, and we can use that to then get to the exports. Here's kind of a more visual depiction. We have the DOS header, the MZ there. We have our DOS stub, and then we have the PE header. Now, one thing that we do note here, so this is the DOS stub, this is the PE header. The PE header has a signature, an ASCII signature, the PE, so that's going to be 4C01. Or I apologize, that's going to be the 5045. And one thing that we notice here is the offset where it begins. So 100 is where that begins. And if we go and look up here, we can see this member right here. And this member here is going to be LFNU. The purpose is to tell us the offset to go to get over this. So we see 10100, and that corresponds to 100. So little endianness 01100, 3 digits. So that is a necessity for that to get to here. Then we have our file header. And then from there, which is very small, and then we have the optional header. Then at the conclusion of the PE header, we get to our data directory, which consists of 16 different arrays, and each has 2 elements. And then down below is the section table. So very broadly, these are some of the main, most important elements as far as loading executable code. So much of this information we've already discussed, but we can review it very briefly. So over here is the start of the PE file format. We have our first 64 bytes. Really, we only care about 2 members. We have the MZ, then we have our LFNU. LFNU allows us to get over the DOS stub, and why? Well, because it's variable in length. Most all of these structures and the different members, so each one of these is a member. These are all a certain size indicated. So it's very predictable. You can know just based off of a specific offset which structure, which member you're in. But when you get to the DOS stub, most of the time it'll say this program cannot be run in DOS. You know, this goes back to Windows 3.1. You know, was back then it was maintaining compatibility and just indicating that, you know, the program could not be run in DOS. Maybe it's possible that some of those early programs could be run in DOS. You know, I don't really know the answer to that because it was so long ago. But regardless, it's part of the PE file format, and you know, there is a good possibility that it could be something different. You know, I've seen a number of different things other than this. And because different messages can take different amounts of bytes, then this is not predictable, and so that necessitates the LFNU. So how do we find LFNU? We've already kind of covered this. So we have the first 64 bytes of the structure, and then it's just simply down there at the bottom. And then over here, again, we can see another depiction. We're in a specific tool. This is a hex editor. The hex editor is called O10. That wasn't very successful, was it? So O10 is going to be the name of the tool there, which is what we see here. So if we are in O10, we can use a template, and then that can map out some of this information for us. So something like LFNU right there can map out to that. And we can see the value there right here. So that's going to be the E8. Most of the values here we don't care about because, again, most of that is just not going to be relevant for us. So once we get that LFNU, it says, I was trying to write with my finger, but I guess it's not enabled here. So anyway, the E0 there is going to be our LFNU, which corresponds to what we see right there, or I guess it's E8. So we can easily see that it's been highlighted for us there. It's one of the great features of O10. Some more slides that bear similar information, but I think it's important to repeat this just because it's so important to understand this, so that we understand how the operating system loads this content, how we can use shellcode to replicate some of this. And additionally, this is something that malware does very often. And it can form a very recognizable pattern. So if you get accustomed to the shellcode that does this type of thing, you can very quickly recognize and know that's what it's doing. So again, we have the 4D5A, which corresponds to our MZ. Then we get down to our LFNU. So we have 00, or we have 0000 01 00, so 100. So that takes us to offset 100. So we have the E0, F0, 10-0, 11-0. Then from up here we have the different, so 0, 1, 2, etc. up until DEF. So we can very easily find which specific one it is. So 1A would be right there. So that's how we get over our DOS stub. From there we have the 5045 and then 2 null bytes. That denotes our PE. So the signature there. So visually we can very quickly recognize that. So what does the PE header contain? Things like our entry point, which is going to be very important. So it provides us with the RVA for the first instruction to execute once the PE loader is ready to run the PE file. We can have other things such as size of image, base of code, number of section, time, date, stamp, characteristics, meaning specifically are you an executable or are you a DLL. So essentially metadata about the file. This is information the operating system needs to know so that when it loads it, it knows where to find the sections. It knows other important attributes such as whether it's an executable, whether it's a DLL, is there ASLR, is there DEP, is there CFG. So again, the PE header portion begins with 54500. Part of what we do with the shell code that we'll see in a future video, and you'll get an opportunity to interact with it, is we will have different structures, the different members, and the distances between the two different elements can come into play. That's part of how we do the walking aspect of walking the PEB or walking the PE file format. So say hypothetically we were at a particular location, the start right here, so it would be offset 0 from our starting point. We note that this is size 4 hex. Why? Because it's a D word. A D word consists of 2 words. A word consists of 2 bytes. So a D word has 4 bytes. Hence being 4 hex, 4 bytes. And this right here, 14, denotes the size of the image file header. 14 hex bytes. That's not decimal, it's hex. So we can disregard that in terms of counting our offsets. And then over here, image file machine is 2 hex. So if I wanted to, for whatever reason, and I don't know why you would want to do this, but let's suppose that you wanted to do so. You wanted to get the number of sections, and you managed to be at the start right here. So you do 4 plus 2, and then you get to the number of sections. And why do you care about that? Because then you could read that value, 6. You would know that it was 6. And of course, you're not going to start at NTD headers, NT header. You would start here at 4D50, and you would use the distances between the different members, the different structures, and taking into consideration things like LF and new in order to parse out, to pull out, to extract whatever piece of information you're interested in. It's the exact same thing that 010 does. It just walks the PE file format in order to get that information. So here we have the PE signature, and then we have the file header, and then we have our optional header. And so here we have the file header. We can see things such as the architecture type, the number of sections, the time date stamp, the characteristics, whether or not it's a PE file or a DLL. So something like a PE File Explorer, PE Studio can go through and parse all this information and extract it. The parts that are relevant, some of it just may not be all that relevant. At least relevant to somebody doing exploitation or somebody doing malware analysis. If you're a operating system, then all of this is pertinent and relevant. And finally, we reach the optional header, which is going to be the last of the 3 structures contained inside the PE header. So we want to get down to the very bottom, to that image data directory. And then one of those, so any one of those inside there can allow us to then get to that particular section. So imports, exports. And then within this section we can see a whole host of other relevant information. Now if you go to MSDN, you can see specific information that describes in detail the significance of each of these. I'll leave that for you as an exercise to the reader or to the student to go and familiarize yourself with some of these. So optional header has three main parts. We have standard files, we have Windows specific files, and then data directories. We can here see some MSDN information on the standard files. Address of entry point stands out as probably being one of the most important here. Image base is something that is also extremely important, so that gives us with the suggested started image base for an executable. So 400,000 is going to be the most common. If something selects into ASLR, then that can be variable. If it's not, then it's predictable. That's very good for us in terms of exploitation, because if there's no ASLR and it's something that we can count upon, depend upon, then we can use those as reliable gadgets or addresses for our ROP gadgets. Something that can come into play that can be problematic can be a null byte at the beginning. So 00. So certain functions can encounter that null byte, and if it encounters the null byte, it could terminate. Doesn't mean that that data, those addresses, don't end up in memory. There's a good chance that they do end up in memory. It just may not be on the stack where it's useful. So on the stack it could possibly be truncated, but it could possibly appear elsewhere in memory. So again, image base is going to be one of those key terms that you really want to be familiar with. And I'm trying to click here. So some of these here, probably DLL characteristics is somewhat interesting. A lot of those here just really is not going to be too relevant for our purposes. Data directory will contain the 16 entries, 8 bytes each. So that can lead us to different parts such as the imports, the exports, resource tables. And there's only 2 members for each. The virtual address and then the size in bytes of the particular data structure. And so here we can see a listing of the different data directories. Export table, so our exports, a DLL, for instance, its purpose can be to provide exports. Very often an executable will just provide main as the only export. Import table if we need to import different APIs. Resources, so we can provide information on different resources such as icons. And that's something that a lot of our reversing tools don't provide too much information on, although it can be important for malware, because sometimes something can hide as a resource. So here we see a visual depiction of the data directories, 16 of them, each being 8 bytes. So we have over here the RVA, so 00, drop the zeros, 20, so 2, D0, and then 00, so in total 2D000, and then following that we have our size, so 00, 00, 18, 1E. So again, it dropped the zeros, 1E, 18. And this is little Indianness coming into play. That's just how we read those. And as I mentioned before, one of the great things about the PE file format is everything is very highly structured, highly ordered. So all these data directories are all at fixed locations. It's not like we have the PE00, the start of the PE header. That's at a unpredictable location because of the DOS stub. Once we get past that, once we get to the start of the PE header, everything after that is highly predictable. And what that means is, because everything is a known quantity, we can count distances, add them together, and be able to get to things that we want. So again, the data directories enable us to identify section headers that are contained in the image section header. And then this allows us to then identify the different sections. A lot of these structures and members just will not be important for reversing purposes or for software exploitation. When it comes to generating shell code, we do care about some of these. The main one we're going to care about is going to be the exports. So our exports is going to be right here, the first one. And if we think about it, why do we care about the exports? An executable, as I mentioned before, typically will provide just main. But if we get to a DLL, then it's going to provide all of the exports. I mean, that's its purpose, to provide exports. So if we can identify something like kernel 32, we want to get to virtual protector or virtual alloc, then we can just walk the PE file format, and eventually we can find that API, and we can get the address for that. That information is not available to us, otherwise it's not previously known from a shellcode standpoint. The executable knows it, but if you are able to insert shellcode in direct execution there, then it's not known. Skip that. So section tables, we can have things like the .text. The .text is going to be our executable code. So that's going to be of primary interest to us. Additionally, we can have things like our data, data, so on and so forth. So the section table, we have that, and then following that, then we have the actual sections themselves. Something like IDAPRO, it's going to care about the .text section. That's really, for the most part, most of what it cares about. And is able to parse that information and to extract the bytes, and from there assemble it into disassembly, which is a very non-trivial task. It's non-trivial because we can have instructions intermingling with data. And so if you start at the beginning of the .text section and generate disassembly based on the presence of the hex opcodes, then very quickly you will reach a point where the disassembly becomes incorrect because you'll encounter data, and then that data will be misinterpreted as instructions, and then the valid instructions that would follow that would also similarly be misinterpreted. So very, very quickly you would get into disassembly that is completely and totally inaccurate. When you have something like IDAPRO, Binary Ninja, Ghidorah, they know how to interpret and distinguish between instructions and data so that this assembly that it generates is correct. There can be third-party utilities like Capstone, which Capstone, all it does is it just generates raw disassembly based on opcodes that you provide it. And something like Capstone can be very enormously powerful. There's something like over 300 different utilities or applications that make use of it, including Radari, which is a very well-known alternative disassembler. And so Capstone can be very extremely relevant and can power lots of things that rely upon disassembly. But if you are making use of something like Capstone, which is a third-party library that's available for many different languages, then you need to be able to use it in a very sophisticated way to provide it with instructions on how to interpret that information, because natively it just simply would not do that. But in any case, IDA is primarily concerned with the executable code, which is going to be the .text, or sometimes .code, which is, I think, Borland. It'll, from there it needs to find the entry point. And then it begins just assembling there, and then it takes into consideration different things such as intermingling of data and instructions. Resources, we see that mentioned. A tool like Resource Hacker is going to be very highly focused on resources, and it can go there and pull out the resources. So here we can see our section table. We have the label of the section, .text. We have the pointer to raw data, so that's the offset from the file's beginning to the section data. And if the section data is not in file, then the value is simply 0. And then additionally we have the virtual address, or the RVA of the section. So a value is 1000 is shown, and the image base is 400,000, then the section will load at 400,401,000. So we see here a depiction of the pointer to the raw data, or the raw offset, which is going to be incredibly useful because it's going to be the offset from the file's beginning to the section's data. As I mentioned, if it's 0, then the section's data is going to be not contained in the file, and it will be determined arbitrarily come load time. So the PE loader uses the value in that field in order to find where the data in the section is in that file. So up to this point, following the DOS, once we got over the DOS stub and we got into the PE header, everything after that point has been at a fixed location. That changes now because we have different numbers of sections, and the sizes of the sections can vary, which is very obvious if you think about it. Something like .text, the size is not going to be a constant because it's going to depend upon the executable code. And so because these are not at fixed offsets, that's why we make use of RVAs, so, the virtual address, so that we have a starting point, the image base. From that image base, we can then acquire the RVA, or the virtual address, and then we can get there. So we have virtual address there. So executable code, we've talked about that. Our .text section, we provide the starting point for execution. The data is going to, we have a number of different things. So the .bss is going to be our uninitialized data, so variables that are declared static and module. We have the R data, or read-only data, so constants, literal strings, things of that nature. Resources, so cursors, bitmaps, menus. Resource Hacker can enable us to get to that. The eData, so our export directory. Import table, information on our imports, base relocations. So when an operating system loads an executable, it goes through and parses out much of all the information that we have encountered. It maps it to memory. It figures out where it's going to execute, and then it simply begins execution. And it takes care of other relevant details, such as initializing the stack and the heap and the initial thread and beginning the process itself. Relocation has become probably a lot less important than it had been prior to ASLR. So in the past, we would have DLLs that would have a preferred image base that would collide. Or it may not be the image base that collides, but there would still be a collision because, you know, a DLL can vary in size. So the preferred image base for one DLL could be smack in the middle of another DLL. Well, how can you resolve those conflicts? So the relocation would deal with that. When we have ASLR, though, so many of them are going to be rebased anyway, so that's much less relevant. Of course, there can be different levels of ASLR. So it could be done at the software level, could be done for system DLLs. We can also have ASLR being enforced by two mechanisms. Number one, Emmet. So Emmet is something that came about in probably 2011, 2012. And it was kind of a hodgepodge of various different mitigations that was made use of to help try to curtail exploits. It has been deprecated. A lot of that is now baked into Windows 10, not as part of Emmet, but it's all just automatically there. So if you're using Emmet, or you can use Emmet on Windows 7, Windows 8, probably some of the Windows Server OSs as well. So using those or Windows 10, then it can automatically change or employ ASLR. So even if ASLR was not intended at the compiler level, it will come into play. And so that ASLR can make exploitation much more difficult unless we have a way around it. There can be things such as memory disclosures or memory leaks, but we won't address that at this point. Export section. This is something that is extremely important to us in terms of shellcoding. As I mentioned, this is going to be one of the main motivations why we need to be aware of the PE file format in detail, because eventually we want to get to this section. We need to first walk the PEB. Once we walk the PEB, we can then walk the PE file format, so the different distances, the different sizes from different members, different structures. Eventually we can get to the export section, and the export section then contains different functions. There can be different ways in which we can get those with shellcode. So we could take the ASCII and we could search for that, or we could make use of hashes. We'll see some of those in more detail later. But from a PE file format standpoint, there can be two different mechanisms. So we can do by name or by ordinal. If you have just simply the ordinal, then it's going to be a 16-bit number that will uniquely identify a function in the specific DLL. So sometimes we may encounter that in malware, and they may do it by ordinal, and that's a way just to make it more difficult to understand, because it's going to be less apparent. Get proc address is going to be an API that it's part of kernel 32. If we get that, then it can return the address of an exported function in the DLL. And we can do that using either the name or the ordinal. So get proc address or get procedure address, procedure being function. Maybe that's a better way to view it, because the proc makes us think of process, and it has nothing to do with process. Get proc address gives us an address. So if you wanted an address to get to a certain function, it gives you that address, so we can call upon that. And we absolutely care about that with shellcode, because if we start somewhere in shellcode, it's going to be position independent. It doesn't know the addresses of everything that has been previously loaded. That information is there for the intended instructions. It's done at compile time, but it's not available to us with shellcode. So get proc address could be one mechanism to bring that about, or simply just walking the PEB in the PE file format. And you can also potentially do a combination of those, so you don't necessarily need to do one or the other. You could use walking the PEB and then walking the PE file format, and then you could call upon get proc address is some in load library. Once you have those two, then you don't need to do everything necessarily by walking the PEB. So that probably would be a more efficient mechanism. We also see this come into play with malware too. So load library and get proc address working in unison together. It just makes it harder for an analyst to figure out what's going on, because if you look in the import address table, or you look at the imports in something like PE Studio, you're not going to see some of these APIs because they're being loaded dynamically with get proc address. In my undergraduate malware course earlier this semester, we looked in great detail at a shellcode that made use of the technique of walking the PE file format and making use of load library and get proc address, and then calling discovering the address for numerous different functions to perform process injection. Had an egg hunter. And of course, a lot of malware does that. It's not just an isolated incident. And so this again will come into play more with when we get into our shell coding, which is coming up pretty soon here. Our import section. So this deals with information on imports. We don't necessarily need to know all of this here. This is all really good information in terms of understanding how all of this works, but we're not going to get into that here. So this has just really provided a very basic introduction into the PE file format. In our next series of videos, we will take a look at how we can use this information with shellcode. And then from there we can dive deeper into the general usage of shellcode, and you'll have an opportunity to create shellcode as well. So we'll chat with you later.